Um, the first speaker in our session is Stefan Henneking from UT Austin, and he'll be telling us about real-time Bayesian inference at extreme scale, a digital twin for tsunami early warning applied to the Cascadia subduction zone. Okay.
All right, thanks, Will, for the introduction, and thank you also for the invitation to present our work here. This is truly collaborative work, involves quite a few people shown here. So there's Shriram, Melinda, and Omar Gattas from UT Austin that work with me, Elise Gabriel with an earthquake scientist from UCSD. And then you've already seen Veselin and Zanio speak this morning from the MFEM team. And then, in fact, in this same session a little bit later today, you'll see John talk about some of the follow-on work that was spawned by this project on some performance-related aspects of the MFEM computations. So just wanted to briefly show this. Most of the work that I will be presenting is work out of this preprint paper here that we put up earlier this year. This paper was selected as a finalist for this year's Gordon Bell Prize, so we get to present this at the Supercomputing Conference this November and hopefully take home the prize. Okay, so what's the motivation here? The motivation for this work is to look at earthquake and tsunami hazards of big subduction zones. And the motivating example that we chose here is the Cascadia region, the Cascadia subduction zone that's located actually not too far from here off the coast of the Pacific Northwest of the US and Canada. So this subduction zone is 1,000 kilometers long. On the west, you have the Juan de Fuca plate, which is subducting underneath the North American plate in the east. And as the plates are subducting, here the red line shown here is roughly where the subduction zone is lying. Those plates are not freely sliding. So the subducting plate is locked in a region that's roughly shaded here in red. And because of the friction forces holding those plates together in place and locked, the North American plate is slowly bulging upward. And over time, that will have the effect that the friction forces at some point will be overcome, a rupture will happen, an earthquake will happen, and that will cause a massive earthquake in the whole region and potentially also displace colossal quantities of water upward as the plate is snapping back toward the ocean, which will result in a big tsunami. The tsunami is going to be traveling east onto the coast and west toward the open ocean, eventually reaching Japan. Now, how do we know this happened? There's a lot of evidence. This was really not known until the 1990s that big tsunamis had happened in this area here. The last big one we know today happened in the year of 1700. And there's a recurrence interval of roughly 300 to 400 years, going back thousands of years that we can show now. And there's various evidence for that. One of them I want to point out, the Nesquin Ghost Forest, actually here on the coast of Oregon. Looked it up yesterday. It's about a 2-hour drive from here. It's a natural site you can visit. It's actually marked on Google Maps. So if you drive by the coast on, I think it's Highway 1, right? You can stop there and take a look. So the current early warning infrastructure that's in place is not really sufficient. Because this hazard wasn't known for a long time, the current earthquake warning systems or tsunami warning systems in place were designed for tsunamis coming from earthquakes generating them in Alaska, maybe even in Japan or somewhere overseas, or what happened in Russia recently. But for an earthquake that happens so close to the shore, you need to be able to react much faster and work with a different type of data set, which is generated in the vicinity of the earthquake. Now, there are proposals to instrument the subduction zone, something like what's shown here. This is one illustration of such a proposal, where one would place sea bottom sensors that take different measurements, such as the acoustic pressure, and connect those sensors by optical fiber cable. And that would enable real-time data measurements that can be used for early warning purposes. So this is what we have in mind as we designed this mathematical framework for tsunami early warning. A lot of the forecasting models that are used, if they are at all model-based, they typically use the shallow water equations, which is a very efficient model for propagating tsunamis in the open ocean. However, in the area of the earthquake itself, where the predominant waves that you're going to see in the sensors are hydroacoustic waves generated by the earthquake itself, by the seafloor shaking, those shallow water equations aren't going to be useful for an inference because it's an incompressible model. It doesn't know about those acoustic waves, so it's not going to be useful for that purpose if you want to use these near-field pressure transients that are generated in the vicinity of the earthquake. I should also mention here this subduction zone in the Cascadia example is so close to the coastline that you would have about 10 to 15 minutes only between earthquake and tsunami inundation for some of the coastal communities, for example, in Oregon. So the Cascadia subduction zone work that we've done really has focused on using this near-field pressure data that's generated in the earthquake area to infer the actual seafloor motion, the spatiotemporal field that's discretized, and it's a high-dimensional parameter field that you want to infer. And once you have inferred that spatiotemporal motion, you can then make predictions about the propagating tsunami. We have employed here high-fidelity models, which it's a linear PDE model of acoustic gravity wave propagation. This is what we've implemented with MFEM, and I'll speak about this in a moment. We're doing this inversion in a Bayesian framework to be able to quantify uncertainties. That's important for decision making for things like evacuation zones or first response. And all of that, of course, has to happen in real time, which here means to be useful for early warning, this should be on the order of seconds in terms of the computation, the inference and prediction. Now, the biggest challenge here is the massive size of this problem. And let me just speak about the forward model. So in the inverse model, we're going to have a forward model and an inference model. The forward model is the PDE model that we solved for the acoustic and gravity wave propagation. It's a linear model, like I said, that's expressed in terms of a first-order mixed formulation here. It has a vector-valued velocity component u, and then scalar-valued pressure p. What's interesting here are the boundary conditions. If you haven't seen this model before, on the sea surface, the coupling to the sea surface gravity wave height is happening through an ODE-type boundary condition where this extra unknown eta comes in. It models the surface wave height. The model itself is driven by a boundary source. That's the model input. So that's the seafloor velocity. Again, that's the spatiotemporal field that couples to the normal component of the velocity on the sea bottom. And then on the outer parts of the domain, we have some type of absorbing boundary conditions that could be something sophisticated like a PML. Here in this talk, I'll just show it for the simple impedance type first-order boundary conditions. This is, like I said, implemented with MFEM using high-order finite elements and fourth-order explicit Runge-Kutta time stepping. The weak formulation that we use here, we integrate the second equation by parts, and the reason for that is that it really lets us, in a very neat way, build in all of the boundary conditions directly into the weak formulation. So there are no essential boundary conditions that have to be imposed as part of the function spaces. The consequence of that is that the proper spaces for conforming discretization here are H1 for the pressure and L2 components for the velocity. In terms of the time stepping operator, this is MFEM, so the way you implement an explicit time stepping here in MFEM, you would define the mass matrix and the stiffness matrix, and that's the operators then that you apply at each time step. You can do this matrix free with partial assembly and so on. And John will talk about this, basically this slide and how this is implemented in detail in his talk and how we can optimize this on state-of-the-art GPUs. Yeah, just for sake of completeness, I wanted to show here the operators associated with those matrices. Now, normally I would go directly into the Cascadia results and the inference model. Since this is a final element talk, I wanted to just show one slide on convergence results. So in a simple setting, like a flat bottom ocean, like a box geometry in 2D or 3D, you can derive analytic solutions depending on the domain size and wave frequencies. So here, for a 2D example, you can see the analytic solutions for pressure, velocity, and surface wave height. So for any given frequency that you excite the system with, there's going to be one single surface gravity wave mode and a finite number of propagating ocean acoustic modes. And then what we can do is some simple convergence tests to make sure that the formulation and the implementation are actually having the convergence rates as expected, and you can show this for both types of modes. Here I'm showing it for the first acoustic gravity wave mode for second and third order elements, and you can see we get, and these are implemented with MFEM, like I said, and time stepping, so you get the convergence rates as expected. Now in the real computations, of course, we don't have a flat bottom ocean, we have a bathymetry that is complicated. The subduction zone, especially depending on where you are in the world in Cascadia, there are some areas where the ocean is going to be 5 kilometers deep, and some areas where it's a few hundred meters or just dozens of meters shallower. This is a vertically exaggerated scale for you to just get an idea of what this bathymetry adapted meshing looks like. The way we mesh this is by making sort of patches on the Cascadia subduction zone and then stitching them together. And I can talk more about this in detail if you're interested, but that's the mesh we use. It's all hexahedral elements. Now, we wanted to test our framework just for the forward propagation, and then I'll show inverse results for that later as well, with actual data from hypothetical earthquake scenarios, which means we collaborate here with Elise's team from UC San Diego. They have a code for dynamic ruptures, so they will compute the actual earthquake, the seismic waves, and then from that we can get the normal velocity components that will be the boundary forcing in our model. So let me just visualize here what a margin-wide rupture scenario on the Cascadia fault looks like for, I think this would be about an 8.7 magnitude earthquake. On the left, you're going to be seeing the vertical displacement. So this is how much the seafloor is uplifted over time. And then on the right, you see the normal seafloor velocity that is underlying that data, and that is the input to our model. So you see that the rupture, when it's starting here in the center, propagates outward. The timescale is shown on the top right there. And propagating both south and north. You see the velocity components on the right corresponding to that. That's the model input, like I said. And you can see there's a few meters up to 1.52 meters of vertical displacement here. And the rupture continues all the way up to about 4 minutes or so in this case. And you see the seismic waves going outward for the large Cascadia domain. And this is the input that we'll be using for the acoustic-gravity code. So I want to visualize that in just a moment. But we'll be focusing on the Cascadia subduction zone area where this model that we're using has this coupled acoustic wave with a gravity wave. Okay, let me go here. So another video. This is from the MFEM computations now. We use fourth order elements here and fourth order Runge-Kutta time stepping. On the left, the 3D visualizations are difficult to do, both because of the size of the data, but also just for the visual appearance of it. So what I'm going to be showing is on the left side, the sea bottom pressure. So that's what you would see on the bathymetry on the sea bottom. So if you had sensors placed there, this is the data you would be receiving. And on the right side, you see the surface wave height. And what you see initially in the beginning here is waves corresponding to the seismic waves propagating outward from the rupture. But then at the same time, you see on the right-hand side here, on the right side, the sea surface wave height, the displacement of the water column upward, which will then eventually propagate as a tsunami. For that, though, you would have to go for a longer time scale. Here, I'm just showing it up to about a few minutes, where at this point, we're mostly concerned with the inference of the seafloor motion. Now, if you wanted to propagate the tsunami all the way to the coastline, you would couple this in the end with probably with a shallow water solver that more efficiently propagates just the tsunami based on the inference you've done. But this is the coupled solve. Now, I don't have a lot of time to go into all of the details of the inference and prediction model, so I'm just going to give you a very brief outline of this and then focus on some of the large-scale results that we've computed with MFEM, which is one part of that inference and prediction model. Now, again, like I said, the inverse problem here is we assume in real time we're given some sparse and noisy pressure recordings from sensors on the seafloor, and we want to infer the seafloor motion from that. The forecasting problem is then once you've inferred that, you want to predict the tsunami wave heights, ideally arrival times, inundation, and so on and so forth. Now, the Bayesian inference model, again, just a very brief outline, just a few of the notational things I'm going to be using here. So the parameters of our model, I've said this a couple times now, this is the parameters we're going to be inferring. There's a field that's discretized for the seafloor motion. I'm denoting it by M. The data D are the point-wise pressure observations, and then we define something called the parameter-to-observable map that basically takes that model input, the parameters, solves the forward PDE, and then extracts the pressure at the sensor locations. That P2O map, parameter-to-observable map, is a linear map in this case because the parameters enter linearly into the PDE. The PDE is linear and the observation operator is 2, and that will be important. There's a similar map you can define for the quantity of interest, which in this case here is the tsunami wave heights. And then in order to the inverse problem, like I said, we phrased this in the Bayesian setting. And without going into much detail, the goal here is to basically characterize the posterior of the parameters conditioned on the data, which is proportional to the prior times the likelihood. And you basically have to come up with some definitions of what you're going to use for the prior of the parameter field. In this case, we're using a Gaussian. That means we don't have a lot of information about the prior of the parameter field. We just assume that it's a smoothing prior, so there's some kind of regularization in the inverse problem. The likelihood here also assumes additive Gaussian noise for the moment here. And if those two are defined this way, and we have the linear P2O map as shown above here, we actually get a linear inverse problem. For that, we can write down the posterior in an explicit form. The posterior itself is a Gaussian. The Gaussian is centered at the map point. That's the point that maximizes the a posterior, the maximum posterior point, and the operator corresponding to the covariance matrix is the inverse of the Hessian. Now, in order to solve this, for a small problem, you can perhaps construct the posterior covariance. For real problems, that's often not possible here. The parameter field will be on the size of 1 billion parameters. So clearly, you cannot compute or store 1 billion by 1 billion matrix. Each computation of a column of that matrix would correspond to applying f and f star once. That's a forward and adjoint PDE solve. So you cannot do a billion PDE solves at large scale. So what you do is you have to figure out a way to compute this map point here and be able to sample from the posterior covariance in some rapid way. And this is where we need some rapid action of the Hessian operator here, which involves these forward and adjoints. There's a whole machinery in place here, and I'm happy to talk with you offline or refer you to the papers about this. But the main component that makes this whole machinery for the inverse problem possible is that we recognize one important property of our system, and that's that the P2O map here represents an autonomous dynamical system, or in particular, a linear time invariant system, which means the mapping from parameters to data can be shifted in time, and it's still the same mapping. In the discretized representation for those maps, what that means is that you get these blocks. Each block here corresponds to a time instance for the parameter and data. And the block here will correspond to spatial discretizations. And then you see these blocks shifted over in the columns. That system is called a block triplets matrix. That has some important implications. First of all, what this implies is that you can store and pre-compute this matrix by only looking at the first block column, and pre-computing those columns can be done by doing as many adjoint PDE solves as there are sensor locations. We have about a few hundred sensors that we are interested in or that we expect to be using here. So that means a few hundred PDE solves at large scale. That's expensive but feasible. The second important implication here is that this type of matrix can be embedded in a block circulant matrix, which itself is block diagonalized by the Fourier transform. And then you can do very efficient MATVEX in Fourier space. So that's the underlying machinery. This whole inversion framework that we came up with to do the real-time inversion feasible without doing any approximations is split into offline phase and online phase. The offline phase has multiple computations as well. I'm just going to focus on the first phase. The first phase is the computationally most expensive phase. This is where the MFEM solver for the acoustic gravity wave problem comes in. And what we have to do here is construct these P2O and P2Q maps, which involves, like I said, a lot of adjoint PDE solves, hundreds of adjoint PDE solves. So in that case, we need a scalable solver and we need supercomputing. And then I will show you results for the whole framework in the end, but just focus on this phase for now. Now, as Sanyo mentioned in his talk already, we for this problem, were also able to use Capitan. So big thanks to Livermore Computing for making this possible and the help we got there. And earlier this year, we ran on the full machine. This is currently the #1 supercomputer based on the top 500 list. Has more than 40,000 GPUs and 5.7 petabytes of memory. I'll also show results for 2 other machines, Alps and Perlmutter. Alps is in Switzerland. It's the currently largest accessible machine for HPC in Europe. with about 10,750 GH200 NVIDIA superchips, and the Perlmutter machine, little bit older, but still 25 on the supercomputing list with NVIDIA A100s. Okay, for the scaling test that I'm showing here that we did, we basically want to look at both weak scalability and strong scalability for the acoustic gravity model. So just looking at the LCUP scaling on the smallest end, we have 85 nodes that we use as the base case, running on 340 GPUs. And then the largest instance that we ran was up to 43,520 GPUs. Corresponding to that, then we have different cases for how many mesh elements we use. And I'll show numbers for the degrees of freedom in just a moment here. So for strong scalability, for all of these three machines, I'm going to be showing here on the y-axis relative speedups. They are relative to the base case in each of these configurations. And then you see the black numbers on the corresponding to each of the scaling results indicate parallel efficiency here. So let's just look at the largest instance, that's LCAP, where we went from 340 GPUs to 43,520. That's an increase of 128x for a number of GPUs. And you get a speed up here of about 100.9. That's 79% parallel efficiency. So we're really happy with these results. And from just a practical perspective, that means you can do about 100,000 fourth order Runge-Kutta time steps here with 400 billion degrees of freedom, or more than that actually, in less than 5 minutes. So very impressive what that machine was able to do here. On the weak scaling side, similarly impressive. We have really good results for all three machines. Again, LCUP being the one that has the most measuring points here, and on the largest end, we're able to fit about 1.28 billion degrees of freedom per GPU. And in fact, John will mention his matrix-free implementation can do even more, but we used a partial assembly implementation here, so that has a bit more storage that we need. So in total, that means we're able to solve up to 55.5 trillion degrees of freedom, which, to the best of our knowledge, is the largest finite element computation that has been reported. I also want to mention that this did max out the machine memory fairly well. We used about 85% of the machine memory here. All right, I have about 3 or 4 minutes left, right? So let me show a few results for the inverse problem, again, just to give you an idea of what the computation times look like, and then some of the results. So for the inverse problem on Cascadia, the mesh resolution is roughly 300 meters. We expect 1 Hertz frequencies here. The wave speed is 1,500 meters per second. The simulation time is 420 seconds, corresponding to the example that I was showing you earlier. The spatial parameter dimension, which is the seafloor discretization, has 2.4 million parameters. But then you also have to basically take that in the temporal direction. So the total parameter dimension here is about 1 billion. We consider 600 sensors, 21 locations for forecasting of the tsunami wave height. So we're going to have to do 621 adjoint PDE solves in phase 1 of this framework. And this is discretized with about 4 billion degrees of freedom in this instance. Just an overview again, visually, just to show you how we solve this. Again, we have this offline phase. This is the orange part here, the first 3 phases that are pre-computations that are done ahead of time before an earthquake ever happens. And then when the earthquake happens, you just execute this phase 4 based on pre-computations of different operators here. And the most expensive part of this computation, like I mentioned, is phase 1, the adjoint PDE solve. So this is where the MFEM-based wave propagation solver is used. So let's look at some computation times. This example we computed on Perlmutter on 512 A100 GPUs, and computing, like I said, the P2O map and P2Q map has all these adjoint PDE solves, 621 solves here, and those solutions take about 538 hours to compute on 512 GPUs, a very massive computation. We did have access to more than 512, so you don't actually have to wait for 540 hours. You can compute each of these PDE solves in parallel if you have access to more than 512 GPUs. The other computations here use this FFT-based MATVEC solver that I was alluding to without going into much detail. It significantly speeds up the Hessian action, which makes those computations possible. The actual inference that happens in real time when you collect the data is rapid. We're able to infer the parameter field in less than a second on 512 GPUs, and also instantaneously predict the QIs at those forecasting locations, which are the tsunami wave heights. To show you the results, let me visualize this with a little video here. So on the left, I'll be showing the true normal displacements on the seafloor. On the right will be the inferred one. And this is, again, over time. So it integrates the parameter field in time. So you see the total displacement. And you can see as the rupture is spreading, it's very nicely captured on the right in terms of the overall structure. You can see the rupture spreading correctly in space and time. So the overall displacement is captured really well in the inferred solution on the right. Again, this is inferred from 600 sensors with some noise added to the measurements, so the synthetic data we're using here. What you can't infer as well is some of the high frequency components, which you see on the right there, and that's because it's a severely ill-posed inverse problem. So all you can hope for in terms of the inference here is the lower order modes corresponding to the overall displacement. But here we're doing a really good job on that, based that we're only using 600 sensors. All right. Also, just briefly showing you the uncertainties here that were computed for the parameter field as point-wise standard deviations of meters of displacement. Those uncertainties in this case, like I said, we use a Gaussian prior, so the only information that really comes in here for the uncertainties is the bathymetry, the sensor placement, and then the boundaries. And you can see that higher uncertainties are at the boundary. You have an observing boundary, so there's less information to do the inference with. And then you see some changes here where the areas become more shallow, and depending on how we place the sensors, which is illustrated here on the left with the black dots. For the QI forecast, this is the last slide on results I have, and then I'll finish up. You can see for different locations, I think I'm plotting it for 8 different locations here, the true QI from the model, and then the predictions based on those inferred solutions. And you also see the 95% credible interval. It's a little hard to see maybe on the projector here around it, that gives you the uncertainty of that prediction. Okay, so let me wrap it up here. I think I'm already maybe 2-3 minutes over time, but I'll be happy to take any questions if Will lets me. Thank you.
With the inverse placement of the sensors right now, you had like a uniform grid. Is there any application of this to like try and predict what the best locations are for sensor placements?
Yes, absolutely. We had a nearly uniform placement here. It wasn't quite uniform, but close to that. We have actually worked on this already, and we have some preliminary results I'm not showing here. So we have, so you can phrase the OED problem, the optimal experimental design problem for sensor placement in different ways. The thing that we've already done, but it's not published yet, is looking at the expected information gain for sensor placement. Of course, you have a potential for placing sensors in many areas, so you have to find some good algorithms to explore that combinatorial space. What we've done so far is some greedy algorithms on that. There are some limitations you also want to take into consideration of where sensors can effectively be placed in the subduction zone. So when you look, for example, at a sensor network that's already in place, like in Japan, they have what's called the S-net that connects sensors similar to what I was showing earlier. You want to, of course, also take some of those constraints into consideration, that placing a sensor in a 4-kilometer deep ocean is much more expensive than placing it in a shallow area. But yeah, we've looked at the OED problem, and that's definitely of interest, as you know, people here in the region are debating the what infrastructure should be put into place to enable early warning, because of course the cost of putting that infrastructure there is significant, and that has to be decided what the best way is to use those resources.
Thank you.
One more question while I transition.
Thank you for the presentation. I have a quick question. That is the inverse problem is unique or non-unique problem?
Sorry, can you say again?
Is the inverse problem is unique or non-unique problem? Like have the one solution or multiple solution? Yeah, how to check it?
It's severely ill-posed by itself, the inverse problem, and in terms of like making it possible to compute a solution here, you have to regularize it, which is where the prior comes in. So you have to take the prior information, which smooths the parameter field in this case, and this is how you obtain a unique solution for the inverse problem. But otherwise, yeah, 600 sensors informing millions of parameters is of course very underdetermined, so there's no unique solution. Yeah, okay. If you don't regularize or put a prior, yeah, that's where the prior comes in.
Yeah, thank you.